All right. So here we are doing freeCodeCamp, scientific computing with Python beta. Learn algorithm design by building a shortest path algorithm. All right. So here's step one. So far, we have already met different data types. Immutable data types such as integers, strings, tuples, and booleans. Mutable data types such as lists and dictionaries. I forgot what those were. What? Oh, there it is. A dictionary is defined by a pair of curly braces. Okay, so it's an object in JavaScript. All right. So we're going to start by creating a variable called copper and assign it an empty dictionary using a pair of curly braces in the same way that we would create an empty list with a pair of square brackets. Okay. Square brackets. Why can't you just say brackets? Anyway, let's do it. So we're going to say copper equals an empty dictionary. There we go. Check the code. Looks good, and submit it. All right, now we're on to step two. Pardon me. So dictionaries store data in the form of key value pairs. Yes. I could have sworn we went over this. Anyway, whatever. A key is separated from a correspondent value by a colon, and each key value pair is separated from the following pair by a comma. Yes, just like an object. All right, so it's just like an object. We've seen this a lot. We're going to add a new key value pair to our dictionary, and we'll use the string species as the key and the string guinea pig as the value. Okie dokie. All right, so let's drop this down one. Let's do species. And remember, this is different. The thing is, it is different from JavaScript objects because instead of just like a variable name over here, we actually have strings as the keys. All right, so that is one difference. Species, and then we'll have guinea pig. Guinea pig. There we go. Let's check the code. Looks good, and submit it. All right, so now we're on to step three. So keys must be unique within a dictionary, and they can only be, and they can be only immutable data types. Okay. So this means we cannot use a list or another dictionary as keys. Very true. Pardon me. So we're going to add another key, age, to our dictionary and give it the integer number 2 as a value. We've got it. Why didn't we have this? Whatever. Let's have comma, and we'll say age 2. Is that an old guinea pig? I don't know. There's that. Let's check the code. Looks good, and submit it. All right, now we're on to step 4. So we can access the data stored in a dictionary through its keys. For example, we've got this right here, and then we'll say my dictionary, and then we'll have name, and that's going to equal Michael right here. So it's just like accessing an object in JavaScript, right? So after our dictionary, we're going to follow the example above to access the species key of copper and print the result. Okay. So we'll do we'll do print. And then inside here, we'll say copper at species. Boom. We got guinea pig over here, right? So let's check the code. Looks good, and submit it. All right, now we're on to step 5. So now we're going to modify our existing print call. What is this? Is the internet off? No. All right, now we're going to modify our existing print call to print the value of the age key. Huh? Print, okay, oh yeah. So we'll just put age here. I don't know why we needed to do all that. Looks good, and submit it. All right, so now we're on to step 6. All right, so we're going to add a new key value pair after declaring a dictionary. We can indicate the key in the same way we would access an... I forgot to put this up here. Look, Codeman S Music. Go check it out. Let's read it again. So step 6, to add a new key value pair after declaring a dictionary, we can indicate the key in the same way we would access an existing key, and set the value of the new key by using the assignment operator. Okay. Yeah. So we would just change it like that. So we would say, no, we would add a new key, right? That's what we're talking about. Let me read. To add a new key value pair after declaring a dictionary, we can indicate yes. The key is the key in the same way we would do this. So yeah, we would say my dictionary and then country equals Canada, and it would just add it in there. Canada? No offense to you Canadians, but why you guys gotta hate on your, why can't you just put America, bro? You're in America. I don't know what it's like to hate myself. I have no idea. What does it feel like? Answer in the comments below. What does it feel like to hate yourself in the place you came from so much? Anyway, so we're going to delete our print call, and then after the copper declaration, we're going to add the key food to our dictionary and set its value to hey. Okay. So delete this. All right. Then after the copper declaration, add the key food. Okay. So we'll say copper at food equals, guinea pigs eat hay? I thought they ate little pellets. Equals hay. Maybe in Canada. No offense to you Canadians. Check the code, looks good, and submit it. Or what if they're just Americans saying Canada and they're just not even Canadians at all? You know what I'm saying? Whatever. I don't care. So now at the bottom of our code, we're going to print copper. Yeah, sure. Print copper. I'm so glad we had this step 7 here to show us how to do something we could have combined into, like, you know, combine 3 of these steps into one. But okay, looks good, and submit it. All right, so now we're on to step 8. So the same syntax can be used to change the value of an existing key. Just before the print call, we're going to access the species key and reassign its value to Cavia porcellus. I guess that's the name of a guinea pig. Let's go see. True. All right. So that's what we're going to do. Access the species key and do that. All right. So let's just take this, drop it thusly, change this to this. Let's grab this thusly, change this to, of course, Cavia porcellus. All right. And there we go. Looks like it happened. Check the code. Looks good. And submit it. All right, now we're on to step 9. So to iterate over the keys of a dictionary, we can simply put the dictionary into a for loop. Okay. The code below would print each key in the dictionary. I'm not saying that word. That's bad for recording. The dictionary. Let's put it like, let's say that. Example code. We've got for loop for I in dictionary. Print I, okay? The code below would print each key in the dictionary. For dictionary in that. So it would print all the keys. Okay. So we're going to replace the print call with a for loop that iterates over copper and prints each key. Okay. So let's do just that. We'll say for. Hold on. Nope, that's not what I was doing. For, nope, that's not what I was doing. For, that's not what I was doing. For, that's what I get for talking smack. I get distracted. For, I in copper, print I. We should have kept that print. Whatever. So let's do that. All right. All right, let's do this. For I in copper, drop it down, press home, tab it over, go in here, and press I. Print I. All right, species, age, food, thusly, check the code, looks good, and submit it. All right, now on to step 10. So if we want to iterate over the values of the dictionary keys, one way is to use the values method. Okay, we're going to modify our for loop to iterate over copper.values instead of copper to look at the output. All right, modify over the for loop to iterate over copper.values instead of copper. Dot values. I guess that's all we got to do. Dot values. Dot caluse. Dot values. Yep, Cavia porcellus. 2 and hey. Looks like it worked. Check the code. Looks good. And submit it. All right. So now we're on to step 11. So finally, if we want to be able to go through the key value pairs, we can use the items method. Gotcha. We're going to modify our for loop to iterate over copper.items instead of copper.values. Okay, so instead of properties, instead of calling these properties, these are called items. Okay. So copper.items. Look at that. We got all these items thusly. Items in tuple form. All right, check the code. Looks good. And submit it. All right, now we're on to step 12. So as we can see from the output item, items creates a data structure. What? Items creates a data structure that stores each key value pair in a distinct tuple. Yes. To iterate over the elements in those tuples, we can add a second loop variable. We do for I, comma j. In dictionary.items, print I, comma j. Let's see how this works. Modify our for loop to take 2 loop variables and print both of them inside the loop body. You got it. For I, comma j. Okay. I, comma j. Okay. So there we go. That's how that works. When you split it up thusly, it takes them out of the tuples and puts them down thusly. All right. Check the code. Looks good. And submit it. All right. Now we're on to step 13. So we can remove a key value pair from a dictionary by using the del keyword. All right. Probably for delete. Huh? Anyway. So here's the example. We've got my dictionary, blah, blah, blah. Del my dictionary at occupations. It's going to delete this item right here. And I bet the comma also. So just before our for loop, we're going to use the del keyword to delete the age key and its value from copper. You got it. So we'll come down here. We'll say del copper at, oh wait, no. Copper at age. And we can see age no longer existicus. All right, here's age, and then now age is gone. All right, so let's check the code. Looks good, and submit it. All right, so now we're on to step 14. So now that we reviewed the basic aspects of dictionaries, we can proceed to build the shortest path algorithm, okay? We're going to delete every line of code after the declaration of the copper dictionary. Okay. See ya. Wouldn't want to be ya. Check the code. Looks good. And submit it. All right. What's this? So here's step 15. Graphs and data structures representing relations between pairs of elements. Ha ha ha. I didn't read that right at all. Graphs are data structures representing relations between pairs of elements. These elements, called nodes, can be real-life objects, entities, points in space, or others. The connections between the nodes are called the edges. Okay, so here's a visual representation of a graph. It's not what I thought a graph was, but I guess it's a different kind of graph. So A, and then it has the edge B, C, D, E, and F are not connected, but whatever. How odd. What an odd concept. Okay. So these are the nodes, real life objects, entities, points in space, and other real life objects. What are you talking about? We're in the computer. Anyway, I don't know what this means, but we'll figure it out. Let's just open our eyes. Let's figure it out. All right. We're going to rename the Copper Dictionary into my graph, and this will represent the graph to test our algorithm. Okay. So my underscore graph. All right. Check the code. Looks good, and submit it. Pardon me. So now we're on to step 16. So for example, a graph can be used to represent 2 points in the space, A and B, connected by a path. Man, I wish they would have kept that picture up. A graph like this will be made of 2 nodes connected by an edge, all right? So yeah, let's look at this. So yeah, 2 nodes connected by an edge. I mean, you can probably see it on yours. We can't see it that well here, but there's a dark black line right here, which is the edge. We're going to replace the existing species key with the strings A. Strings A. There's only one string there, bro. This is like, the thing is, look, the further we get into it, the less edited it's going to be, because they're really only considered. These guys are really only concerned, and I know this because it reflects on my channel too. They're only really concerned with the beginnings, all right? This stuff's already done, but they're really only concerned with the first parts of these. That's why this one keeps getting updated. That's why this one got added. That's why this keeps getting updated. But you go down here, these will probably never get updated, because they know by their analytics, by these guys' analytics, they know that by the time they get down here, either they quit or they got it and they can just fly through, you know, one or the other. But regardless, yeah. Strings A. The strings A. Anyway. So then we're going to replace the correspondent value with the string B to represent the connection between the A and B nodes. Okay, so this is going to be B, I guess. Little loopy, but whatever. Check it, looks good, and submit it. All right, now on to step 17. Give me a second. All right. So now we're going to replace the age key with the string B and set its value to the string A. Okay. B and the string A. This one's going to get me confused, I bet. To represent the connection between the nodes in both directions. Okay. Okay. Let's make this like this. All right. Check the code. Looks good. And submit it. So now we're on to step 18, and we're going to add another node connected to B to our graph and call it C. We're going to modify our existing directory to represent this arrangement. We're going to add another C to my graph and give it the value of string B. We'll also change the value of the existing B key into list A, C to represent the multiple connections of our B node. What? I thought it couldn't be a list. I thought the keys couldn't be lists. I thought they had to be immutable. Or no, are lists immutable? I don't know. We'll see. So we're going to modify our existing dictionary to represent this argument. We'll add another C key to my graph. Let's do that first. C. And give it the value of B. Okay. Also, we're going to change the value of B into it's the value they want to change. Okay. So let's change this into a list. Oops. And then we'll add the C to it while we're at it. So comma C. That should be what they want, right? Makes sense, right? Check the code? No. What does it say here? Invalid syntax. Perhaps we forgot a comma. Oh, yeah, we did. Boom. Check the code. Looks good. And submit it. All right, now we're on to step 19. I'm looking at this thing, right? So we're going to add one last node D, which is connected to A and C. We'll modify our dictionary to represent this structure. Again, we'll use a list to represent multiple connections. Okay. D. Hold on. D. Hold on. Hold on. Hold on. Hold on. D now equals A and C. Well, let's just grab this, huh? Why not? No, not like that. Like this. All right. D is connected with this. D is connected with A and C. Do we need to change A to be connected to D? I think so. So let's wrap this up in parentheses in the thing. And let's say B, comma D. Whoa. Comma D. And then add a comma. And we're going to have to add this to, we're going to have to do the same here. And do B and D as well. All right, so let's grab this. Drop it. And then add another comma here. And I think that's what they want. Check the code, looks good, and submit it. All right, now we're on to step 20. I'm drinking soda, and so it's like ruining my, it's like making me salivate, but whatever. I don't think you needed to know that. Whatever. Step 20. So a graph is called a weighted graph when its edges are associated with weights, representing a distance, time, or other quantitative value. Okay. In our case, these weights will be the distances between each node or point in space. To represent a weighted graph, we can modify our dictionary using a list of tuples for each value. Okay. The first element in the tuple will be the connected node. And the second element will be an integer number indicating the distance. What? To represent a weighted graph, we can modify our dictionary using a list of tuples. Okay, so we're going to turn this into a tuple probably. We'll modify my graph A into a list of tuples. Okay, a list of tuples? Considering that the AB distance is 3 and the AD distance is 1. Okay. So let's wrap this in parentheses. I think this is what this is saying. All right. No, not like that. Like this. So we've got B, and the distance between B and A is 3. How's that? I thought they were right next to each other. What? Why is the AB distance 3? And the AD distance is 1. I think this is what they want, but it doesn't make sense to me. Is this just an arbitrary number? I don't know. Let's click, check the code, looks good. And aren't these right next to each other? I don't know. I don't know. Do we need to go back to that one picture? What was that picture? Nope. 14, 15. There we go. Look, they're like right next to each other. How's this? And this one's 1, 2. I don't get it. I honestly, I don't know what's going on, but whatever. We'll figure it out. Remember, we're just opening our eyes now. These guys are throwing stuff at us that we've never seen before. Let's just go through it and we'll solidify our knowledge when we go over to Code Wars and actually get some real practice in. All right. So here's step 21. So now we're going to modify the mygraph, what is this thing called? Dictionary, into a list of tuples where the first element in the tuple is the connected node and the second element is the distance and the BC distance is 4. Okay, so this one's going to be 3, this one's going to be 4. All right. So let's wrap this up. This will be 3 because we know that because it's 3 up there, right? And then this one's going to be 4. Not like that, though. Like that. Check the code, looks good, and submit it. All right, now we're on to step 22. So in the same way, we'll modify the remaining 2 lists considering that CD distance is 7. Okay. CD distance is 7. Makes sense. Makes sense. Okay. I feel like I had a dream about this one time. All right. Let's throw this one down here and let's change the C into a B. All right. DC is going to be 7. So let's, what are we doing? It's D. We've got a D right here. So let's just take this D and then change it to 7. All right. Now we've got A. So let's take this A and change it to 1. And then we've got C, which will be 7. All right. So let's take this, drop it, and make a 7 out of it. All right. And that should be what they want. Check the code, looks good, and submit it. All right, now on to step 23. I guess these are just arbitrary distances, honestly. So now we're going to start developing the algorithm to calculate the shortest path between each node in our new graph. Yeah. So we're going to declare an empty function called shortest path, and we'll use the pass keyword to fill the function body. Okay. So we'll say shortest path, and then we'll do pass. Def, don't forget def. Go to the end, bring it down, and then say, what were we saying? Pass. All right, so let's check the code. Looks good, and submit it. All right, now we're on to step 24. So the algorithm will start at a specified node. Then it will explore the graph to find the shortest path between the starting node or source and all the other nodes. So for that, our function needs 2 parameters, graph and start, okay? We'll add them to the function declaration. Let's do that. Graph, whoops, and start. Not like that. All right, like that. Check it, looks good, and submit it. All right, now we're on to step 25. So to keep track of the visited nodes, we need a list of all the nodes in the graph. Okay. Once a node is visited, it will be removed from that list. So now we're going to replace the pass keyword with a variable named unvisited and assign it an empty list. All right, so we'll do unvisited equals an empty list. All right, let's check the code. Looks good, and submit it. All right, now on to step 26. So now we're going to create a for loop to iterate over our graph, and we'll use the append method to add each node to the end of the unvisited list. Create a for loop to iterate over our graph, and then we'll use the append method to add each node to the end of the unvisited list. All right, so we're making a for loop. For. Use the append method to add each node to the end of the unvisited list. So for I in my graph, okay, let's say that. And then what we're going to do is let's do unvisited dot append my graph at I. Hopefully that's what we're doing. Let's check the code. Nope. For to iterate over my graph, not inside of the diff. What? Unvisited dot append my graph at I. Is that not right? Or do we just do I? Because it's not, okay, yeah, it's not a range, so it's probably just I. Let's check it. No. Over graph inside the shortest path. Graph. Oh, graph right here. Yeah. Check the code. Looks good. And submit it. Okay, node in graph. Well, whatever. All right, so now we're on to step 27. So while the algorithm explores the graph, it should keep track of the currently known shortest distance between the starting node and the other nodes. So before our for loop, we're going to create a new variable named distances and assign it an empty dictionary. Okay, before the for loop, we'll create a new variable named distances right here. So distances equals an empty dictionary thusly. No, thusly. All right. Let's check the code. Looks good and submit it. All right. Now on to step 28. So the distance from the starting node is 0 because the algorithm begins its assessment right from there. So after appending node to unvisited in our loop, we're going to create an if statement that triggers if the node is equal to the starting node. Then we'll assign 0 to that node inside the distances dictionary. After appending node to unvisited in our loop, we'll create an if statement. Okay, so outside the for loop? In the loop. We'll do an if statement. Okay, let's do an if statement right here. That triggers if the node is equal to the starting node. If node equals the starting node. Huh? If node equals start. All right, cool. And then assign 0 to that node inside the distances dictionary. So distances at node equals 0. Hopefully that's what they're saying. Let's check the code. All right, looks good and submit it. Lucky guess, lucky guess. So now we're on to step 29. So at the beginning, all the other nodes in the graph are considered to be an infinite distance from the source node. Okay. Because the distance has not been determined yet. Okay. We're going to create an else clause and assign an infinite value to the node in the distances dictionary. Okay. Else clause. For that, we're going to use the float function with the string inf, turns out, as argument to the, to generate a floating point number representing the positive infinity. Okay. So we're going to do an else right here. Else. We're going to assign an infinite value to the node in the distances dictionary. So distances.node, let's take this, equals float inf. Float inf. All right. Yeah, we're definitely going to have to go to Code Wars to get this because there's no way I'm going to remember to do this stuff. You know, after what, how long is it going to be till we see this again? Like a week, 2 weeks, you know? Looks good, and submit it. All right, now on to step 30. So after our for loop, we're going to add a print call and pass in the following string to see the values of the variable we've created, of the variables we created, right? So after the for loop, we're going to add a print call. So let's get out of this for loop. Right here, print. And then we'll do an f string, unvisited. And then we'll do the embedded expression of unvisited like this. And then we'll do a line break, a number break, a line break. I don't remember what the in was actually for. So distances. And then we'll have, what is the prop? Well, let's finish this and then we'll say distance. Oh, and then cap it off with a, whatever that is. Single quote, all right? Check the code. Come on. Okay. F string, unvisited. Unvisited, unvisited, in. Distances. There should be a space, huh? Okay, and submit it. All right, so now we're on to step 30, but that's going to be it for now because we're a little bit over halfway. We'll do step 31 through step 59 later. Be sure to go check out Codeman S Music if you get a chance. It's 8:30. Well, just check it out. I'm going to be live over there 8:30 p.m. Central Standard Time, Saturday through Thursday nights. All right. Other than that, there's all that, and we'll see you next time.